This is a 6.5 horsepower, 196 cc, 4-stroke gasoline engine. Mounted to the block of the engine is the carburetor, a device responsible for mixing fuel with air ahead of the combustion chamber.
This diagram shows an axial cross-section of the carburetor. The airflow channel across this device is the venturi. A choke valve at the opening of this channel controls the inlet flow, followed by a converging region that concentrates air into the throat. A throttle valve behind the throat controls the outlet flow. Below the carburetor is a fuel reservoir. A localized pressure drop at the throat draws liquid fuel from this reservoir into the air moving through the venturi. The resulting mixture of fuel and air exits the carburetor on its way to the engine intake manifold.
We begin our dissection of the carburetor by making 3 assumptions that simplify the analysis. First, we assume the flow through the carburetor to be quasi-one-dimensional. Secondly, because the Mach number describing the speed of air moving through the venturi reaches a maximum of about 0.2 and thereby never exceeds the critical value of 0.3, we assume that the flow is incompressible. Third, in the converging region and throat of the venturi past the choke valve, we assume the flow to be inviscid.
Under normal operating conditions, the pressure of air at the inlet of the carburetor is atmospheric. The pressure of the fuel-air mixture at the outlet of the venturi is controlled by the combustion chamber and can be approximated as 1/3 of an atmosphere. We denote this outlet pressure P-combustion. The difference in inlet and outlet pressures generates a net force acting on the air to drive flow through the carburetor.
By conservation of mass, we can relate the cross-sectional area of the inlet to that of the throat. As a cross-sectional area of the throat decreases, the speed of the flow through the constriction must increase. We then apply Bernoulli's streamwise equations to conclude that an increase in flow speed at the throat results in a decrease in pressure.
Below the venturi, the fuel reservoir is fitted with a flow valve. To maintain atmospheric pressure, a net force resulting from the pressure drop at the throat draws fuel from the reservoir and into the flow.
The geometry of the carburetor is specifically designed for 2 purposes. First, the converging region at the inlet minimizes viscous losses as the speed of the flow increases. Secondly, the cross-sectional areas and resulting pressures are tuned to stoichiometrically optimize the ratio of fuel to air for combustion. Ideally, the fuel-to-air mixture remains constant as mass flow rate through the carburetor varies during engine operation.
In an unrestricted open channel, fluid flow is driven by a pressure difference between inlet and outlet. The distribution of this pressure is linear. The pressure drop associated with an increase in speed is described by Bernoulli's equation, and the viscous losses along the channel are described by the viscous dissipation equation.
By placing a throttle valve into the outlet channel of the carburetor, we can control the viscous losses at the outlet. This generates a greater pressure drop due to viscous losses and a greater loss of kinetic energy to heat. Using the valve to manipulate the speed of the fluid controls the flow rate of the mixture entering the combustion chamber, and consequently, the power output of the engine.
Similarly, we can add a choke valve to the inlet channel to manipulate the viscous dissipation and the pressure in the converging region. By restricting the flow at the inlet, significantly more fuel is drawn into the flow across the throat, a configuration most suited for starting a cold engine.
In combination, the geometry of the venturi and its valves control the mixture of fuel and air delivered to the engine. The carburetor, a purely mechanical device, is a marvel of fluid mechanics and an important subject of analysis.